All right, in this lesson, we are going to graph log functions. And so just like with exponential functions, we can have different parents depending on the base. And so the first parent function we're going to look at is common log, which is log base 10. And so just thinking back to our exponential unit, when we are graphing exponential functions, let's just look at y equals 10 to the x. We could make a table of 3 points looking at where x was -1, x was 0, and x was 1. Anytime we plug in 0 to an exponential function, anything to the 0 power is 1. And then if I plug in 1 for x, I just get the 10 back. And if I plug in -1, I get 1 over 10. And so in general, if I have y equals b to the x, I would have -1, 0, 1. I would have 1 at the 0, and then the base at 1, and then 1 over the base. And so with log, if I were to change this to logarithmic form, the base is 10 of y equals x. So log base 10 of the y equals x. And so what you'll notice is the input of an exponential becomes the output of the log. And the output of the exponential becomes the input of the log. So your x's and y's, inputs and outputs, just switch places. And so for our log base 10, the table of points for this function, you're going to have the -1, 0, 1 in the y column, and you're going to have the 1/10, 1, 10 in the x column. The x's and y's just switch places. And so if we were to put this on the graph, we would have 1, 0, and then we would have the point 10, 1, and then the point 1/10, which is really close to the x-axis or the y-axis, and -1. And so just like exponential had a horizontal asymptote that we were moving away from, we had a y-intercept, and then this next point was 110, and then we were cutting in tenths each time. And so we had a horizontal asymptote. So now that pattern, we're getting closer and closer to the y-axis. And so that's why it says there's a vertical asymptote at x equals 0. This is the x equals 0 line. The y-axis is the x equals 0 line. Just like this is the x equals 1 line, x equals 2 line. And so think of which axis it's crossing when you're writing that equation. And so our graph looks kind of like exponential, but flipped. And so you're always going to have a vertical asymptote. And I like to think of it as it kind of looks like square root. So if you start at just the x-intercept, it goes up to the right, but then he has a tail that goes down towards the asymptote. Okay, and so the domain of all your log functions are going to be either to the left or the right of your asymptote. This particular function is to the right of the asymptote, and so we're starting at 0 and going to infinity. The range will be all real numbers this time. Exponential had a domain of all real numbers. Log has a range of all real numbers. And so you never have to think about the range. It's going down forever. And then even though it looks like it's not going up, it actually is going to continue going up, just very slowly. And so the x-intercept here is what we're going to want to track each time. And so this x-intercept is 1, 0, but it's not always easy to find the x-intercept because as we transform the log function, it could move up, down, left, or right. And so we'll see some transformations, and then I'll show you how to find the x-intercept algebraically. Okay, and so now we are working with log base 3. So you could use this table of points and just transform the table each time, or there's actually a pattern to the points. And so you're always going to want to graph the vertical asymptote first. And then your first significant point is the x-intercept, and it's always going to be 1 away. And then your next significant point is going to be the base away. And so in this case, it was 10. And so if I'm going to graph the parent function of log base 3, I'm going to graph it in green. So log base 3 of x. He's going to have a vertical asymptote at 0. And then the x-intercept is going to be 1 away. The next significant point is going to be the base away. So now I'm going to go over 3 units to get my next good point. And so if no transformations happen, it's going to go up to the right, down towards the asymptote. So think of square root. It goes up to the right, and then it has a tail down towards the asymptote. That's default. That's the parent. And so this particular function, we are reflecting it across the x-axis. So you can abbreviate that r sub x, reflect across the x-axis. So this x-intercept, it's sitting on the x-axis. It's not going to move. But this next point, it's going to reflect down to the bottom. And so my 3 away point is now beneath the x-axis. And so the tail goes up towards the asymptote, and then we go down to the right, kind of like when we reflected square root. And so this red is the new transformed function. His domain, he's still to the left of the asymptote. The asymptote didn't move, and he's still not left, to the right of it. Sorry if I've been saying that. To the right of the asymptote. And then range, all real numbers all the time. Okay, and then our x-intercept is pretty easy to see on the graph. It didn't move. It's still going to be 1, 0. All right, so for this next one, we're working with log base 4 plus 2. And so let's just start with looking at the parent function, log base 4. And so he has a vertical asymptote at x equals 0, an x-intercept that's 1 away, and then his next significant point is going to be 4 away because we're working with base 4. And so he's going to go up to the right and then tail down towards the asymptote. And so the transformation here is just up to. And so our x-intercept is going to move up to. Our other significant point is going to move up to. But shifting up or down isn't going to shift the location of the vertical asymptote. So still up towards the right, down towards the asymptote. And so here our x-intercept isn't going to be a nice, pretty number. And so we'll skip that and come back to it. But our domain, we're still to the right. So 0 to infinity. And then the range still all real numbers, negative infinity to positive infinity. So same if we move it down. Here we're back to log base 10. Remember, if there's no subscript, your base is 10. So I would have my vertical asymptote, let me use green, at x equals 0, just like we graphed above, 1 away, and then my next good point will be 10 away. I hope this is 10. Yes. And so up towards the right, tail down towards the asymptote. And then shifting down 4. Anytime you have a plus or minus outside the log, that's up and down. And so we're going to move our x-intercept down 4 and then move our other significant point down 4. And so again, the asymptote doesn't move. You can shift a vertical line up and down all day long. You're not going to see it move. And so domain still 0 to infinity. And then range would be still negative infinity to positive infinity. So here, our x-intercept is going to take us forever to reach the x-axis. And so we'll find that a little bit later algebraically, but it's not going to show up on this graph at all. Next, we have a number being added inside the parentheses. And so remember, inside is happening to x, so it's happening in the left and right direction, and it's backwards. Your x is a liar. So this looks like it should be right 1. It's actually going to be left 1. And so let's start with the parent function, and then we'll move it left 1. So here we're working with base 2, and so default setting is vertical asymptote at x equals 0, 1 away, and then our base is 2, so our next good point is 2 away. Up to the right, down towards the asymptote. And so now when I shift this function left 1, the vertical asymptote does move. It's now at negative 1. Let's see if I can get a straight line. And then our x-intercept shifts back 1, and then our other point shifts back 1. And so up to the right, down towards the asymptote. And so this is going to change our domain. We're now going from negative 1 to infinity. We're still to the right of this asymptote, but the asymptote has moved off of the 0 into the negative 1. And then range, all real numbers all the time. And so here our x-intercept is easy to find. We can see it's 0, 0, the origin. And then here, this next graph is going to move right 2. And so let's start with the parent function. We're back to base 10. So default, x equals 0, 1 away, and then our base is 10, so we're gonna go 10 away. And you don't have to graph the parent each time if you want to just visualize it. I think it's helpful to graph it each time. And then now that we're moving right 2, the vertical asymptote is now at x equals 2. And so I should be writing these in. X equals negative 1 is the vertical asymptote. Here, our vertical asymptote each time was still x equals 0. And so now our vertical asymptote is x equals 2. And then our 1 away and then 10 away point is going to be off the grid by 2. But still up to the right, down towards the asymptote. So that changes our domain 2 to infinity, and then negative infinity to infinity. And something I haven't mentioned is we're always going to be using a parenthesis here, because remember, we never touch this asymptote. Even though it gets infinitely close to it, it never actually touches it. All right, and so these next examples, we're going to have multiple transformations. And so I'm going to start with the parent again. And so working with base 5, default setting, x equals 0 for the asymptote, 1 away, and then our base is 5 away. So 1, 2, 3, 4, 5, up towards the right, down towards the asymptote. So now we have 2 transformations. We have a left 3, because that's inside happening to x, and then we have a down 1. And so I'm going to start with the left 3, because that moves the asymptote to negative 3. For our vertical asymptote. And then our 1 away point. And then we're going to have our 5 away point. And then this is also shifting down. So I should, before I graphed those, I should have shifted them down. So we're going to shift them left 3, 1, 2, 3, down 1. Left 3, 1, 2, 3, down 1. And so down towards the asymptote, up to the right. So here we do have a nice x-intercept, it's 2. And so transformation left 3, down 1. Domain, we're still to the left of the asymptote, which is now at -3. Going to positive infinity. Range still -infinity to positive infinity. All right, last one. We have log base 10 again. So let's get the parent. Default, x equals 0. And then 1 away from the asymptote, and then count 10 away from the asymptote. And always going up 1 unit to get that other point. And so down towards the asymptote, up towards the right. And so this time we have a reflection across the x-axis. We're gonna have to do that first. And then we have a down 3. That -3 is outside the parentheses, outside the log. Sometimes they won't even have these parentheses. And so just be very careful. If it's not inside the parentheses, it's outside. If they want it inside, they would have to add the parentheses. So if you just saw log x -3, you're only allowed to add parentheses around the x. If they wanted it to be log x -3, they would have to include the parentheses. All right, and so we're gonna do the reflection first. And so my x-intercept isn't going to move, but this point is gonna move down here. Okay, and then we have to move these 2 points down 3. Get that green point back. Okay, so take this red point and move it down 3, down 1, 2, 3. So get rid of those. Reflect, then move down. You don't want to shift something and then reflect it. Your points will be off. Okay, and so because of the reflection, we're going down towards down to the right, and his tail is going up towards the asymptote. Okay. And so reflecting and shifting up and down didn't move the asymptote. The vertical asymptote is still at x equals 0. And we're still to the right of it, even though he's upside down. And then range, always all real numbers. And so here we have an ugly x-intercept as well. And so to find the x-intercept algebraically when you have a situation like this, let's go back to the other ones we skipped. So here, to find the x-intercept algebraically, you just plug in 0 for the y value and solve for it. And so this is why we had to solve equations before we started graphing. And so your first step would be to subtract 2 from both sides. And then once you've isolated this log, you're ready to convert to exponential form. So the base is 4 to the -2 equals x. 4 to the -2 equals x. So we have our x isolated, we just need to simplify that. So 4 to the -2 power is 1 over 4 squared, which we know is 1 over 16. And so our x-intercept is 1 over 16. And then remember, that's an x value and y is 0. Get in the habit of writing it as an ordered pair. And so it's going to be really, really close to 0. Okay, and then for this next one, plugging in 0 for the y. And we're working with base 10 if you want to keep writing that. And so we would add 4 to both sides first to isolate the log, and then we would convert. So our base is 10 to the 4th power equals the x. 10 to the 4th power equals the x. And so remember, when you see 10 with an exponent, that's how many zeros you have. So that means 4 zeros. And so that's our x-intercept, 10,000, 0. That's not on your graph. Okay, and then for this next one, forgot to write the right 2. Plugging in 0 for the y, log base 10 of x minus 2. And so there's nothing to isolate here. Our log is already by himself, so we're ready to convert. 10 to the 0 power equals x minus 2. Anything to the 0 power is 1. Add 2 to both sides, we get x equals 3. So our x-intercept is 3, 0, and that was on our graph. So that was pretty much unnecessary, but it's good to check. And then for the last one, plugging in 0 for y. Add 3 to both sides. Do that first. And then you're not ready to convert yet. You still have this -1 outside. And so if you want to fill in the -1, you have to get rid of that. You have to divide both sides by -1. And so that gives me -3 equals log base 10 of x. Now we're ready to convert. 10 to the -3 equals x. 10 to the -3 equals x. So that's 1 over 10 to the third. And 10 to the third has 3 zeros. That's 1 over 1,000 as our x-intercept. 1 over 1,000, 0. And so that's so close to the asymptote.